Hi, my name is Emily Pfeiffer, and this is my Module 4 final project for the Flatiron Data Science Bootcamp online. This project was on computer vision. It was my first image classification project. Over here, got a brief table of contents, a little preview of what's to come. So I decided to work with the Fashion M-NIST because I thought it'd be pretty good level to challenge myself for my first image classification project. When I was looking for a sensible data set to work with, the original M-NIST, which I think is about handwriting, it seemed to pop up everywhere. And so when I was looking that up, I found that it really has been everywhere, and it's been used by everybody. And there are a couple criticisms on it, that it's a little too easy and everything. But I did think, since it is kind of one of the staples of data science, it should be something I should explore. But again, I wanted to challenge myself, so I settled on the little cousin of it, which is the Fashion M-NIST. The Fashion M-NIST is a data set just comprised of about 10 different articles of clothing. It's about 60,000 images. They're all 28 by 28 and black and white. And like I said, there's about 10 different classes. You've got trousers, sandals, sneakers, etc. I was able to download it directly from Zalando's Research GitHub. So the first thing I did was just import the necessary libraries. Pretty standard stuff, pandas, NumPy, Matplotlib. Keras was the new kind of libraries that I hadn't worked with before. So imported those. The dataset had already been split into a test set and a train set. I think, like I said, there were 60,000 images in the train set and 10,000 in the test set. So I just opened them both. Previewed them, everything looked pretty good. You see we've got our little label column right here indicating which class or article of clothing each image was. And the first thing I did was I just removed the target from each of those. And, I knew this data set had been worked with pretty widely and was already pretty good to go, but just for a sanity check, I did check for null data, and that was about the extent of my data cleaning on this data set. As you can see, we didn't find anything. So I moved straight on to EDA, exploratory data analysis, which was also pretty different from the classification projects I had done previously because there really wasn't much EDA to do or exploration within the data that I could complete until after I'd run the model. So over here I did decide, I just ran a quick distribution of classes. I saw that everything is pretty even, and I got the hard numbers to back that up. So there's about 6,000 images in each class. And I thought it might be worth it to look at pixel distribution. So I just took a subset of about 1,000 images and got a little histogram of the distribution of pixels. You can see we've got 1 to 255, which makes sense. That'll of course come back up in normalization later. And the last part of my EDA was just viewing these resized images from their flat array. So I went ahead and took a look at those. As you can see, they're a little bit blurry, but you can pretty much tell which each thing is. It looks pretty expected, although some of them are a little bit easier to tell than others, so good luck to our model. And then I moved right on to data preparation. So the first thing I did was normalize the data, dividing by 255, since the pixel values are integer values between 0 and 255, which was also reiterated by the pixel distribution graph that we made. And then, like I said, we already had a test and a train set, but when working with Keras, it's also good to have a validation set. So I just used the built-in sklearn function for test train split on the training set, and I took about 20% of that and made a little validation set from that. And then moved on to label encoding. So on our target variables in the train, test, and validation set, I just one-hot encoded them since it's not a binary and our model wouldn't run on it as is. And then I moved on to reshaping the data. Since our images were 28 by 28, but they've been stocked into the data frame as 1D vectors of 784 values. Our next step was just to reshape them into 28 by 28 by 1 3D matrices. Keras does require the extra dimension in the end, that little one over there, to correspond with the channels. Since it's grayscale, we only needed one. But if they were color, if it was RGB, we'd have 3 channels to correspond to each of those. But I digress. So I reshaped those, and then I just did another little sanity check, made sure everything looked good. As you can see, our Y target variables have been label encoded, so they've got a different shape. That makes sense. And I moved right on to creating our convolutional neural network. So to define the CNN, I used a sequential model, which is formed just by adding each layer at a time, as you can see down here. I just manually added those. The first layer was a convolutional layer, which essentially just applies a set of trainable filters to the data. It works by just transforming part of the image set by the size of the kernel using the kernel filter, and the kernel filter matrix is then applied to the whole image. So in this layer, I set the activation to ReLU. I'm not exactly sure how to pronounce that, but ReLU. Which is just to include a rectifier activation function that can inject a little bit of nonlinearity into the network. And I also set the initializer to He normalizer, which initializes the weight vector to have an average of 0 and a variance of 2 divided by the number of features feeding into the layer. And the next step was just adding a downsampling filter, which I was able to do through this MaxPool 2D pooling layer. And then I added a couple dropout layers in here, as you can see, increasing the size at the end. I had 0.25, 0.25, and then 0.5, which is just a regularization method used to reduce overfitting. And then we had our little flatten layer over here, which converts the final features into a single 1D vector, so we can make use of the fully connected layers after all the convolutional and pooling layers. And then finally I had the dense layer, which is to output the probability distribution of each class. And then our next step was compiling the model. So we had to add a loss function, an optimizer, and a metric function. Metric function, that was accuracy. We knew we wanted to evaluate that. And then for the loss function, I chose the categorical cross entropy one, which I think is a pretty standard loss function to use on just categorical classifications or anything that's non-binary. And the optimizer that I used was the RMS prop, which adjusts the AdaGrad method to minimize the decreasing learning rate. Got a little summary to verify everything looked pretty good. And then I went on to fitting our model. I decided to have a batch size of 300 and use 80 epochs. I started with 60, but I found, of course, when you increase the size, you can also increase the accuracy. I would have gone to 100, and I might in the future, but this was just about as long as my computer, I think, wanted to take at this moment. So this did take a while. This took, I think, about 5 hours. Yeah, it took almost exactly 5 hours. I did run it overnight. So evaluating our model, I went and got both the loss and the accuracy. Our test loss was 0.18, which is pretty low, and our test accuracy was about 93.5, which is also pretty good, especially for a first run through. I did go ahead and plot the training and validation loss functions. So you can see they look pretty similar to each other over here, although our training loss was a little bit lower than our validation. And again, with accuracy, again, they seem to pretty much mimic each other, but again, our training did end up getting a little higher on the accuracy than our validation over here, but they do seem to look pretty similar. And then I went ahead and saved that model. But I wanted to just, since it is my first computer vision project, I wanted to make sure I was doing it justice. So I went ahead and I used the image data generator to basically augment our data and just increase it so we could, quote unquote, artificially increase the size of our data set so that we'd have more data to work with and thus improve the score of our model, hopefully. So I kept a lot of these features to their defaults. As you can see, a lot of them are set to false. The ones that I did change were the ones I thought would make most sense. Like, for instance, I didn't really think my model in the future would have to come across a vertical flipped picture, you know, of like an upside down pair of pants, but horizontally flipping the images I thought was kind of relevant, because I thought you would be able to see that in the real world. And the rest of the parameters that I adjusted were mostly just couple like slight shifts on the images, you know, seeing maybe part of it's cut off or a little off center, zooming in, etc., rotating it a little bit. So keeping our images pretty similar, pretty standard, but, you know, just making it so that our model could have to jump through a few hoops. So once again, 80 epochs, batch size about 300. I didn't fine tune the model at all, I just kept it as is. And I went ahead and ran this again, as you can see here. And this took about 5 hours. So unfortunately, our test accuracy did decrease. It went from about 93.5 to 92.5, and our test loss went from 0.18 to 0.20. But overall, these scores are still pretty good, and you know, these numbers don't represent everything. So I did go ahead and I plotted the loss function again. As you can see, you know, while our loss didn't get as low as it did in the first time we ran the model, the validation curve looks a lot better than it did in the last graph. It starts a lot lower, it consistently stays a lot lower. As you can see, it is decreasing, but the slope is a lot more slight than our training loss one. But of course, that's expected when it already started so low at about, you know, 0.23 over here. But it was decreasing, so it did demonstrate some optimization. And then moving on to our accuracy graph, again, as in our first model, you know, these curves look really similar. In this one, our validation data, the orange line over here, it did start up a lot higher than our training data, and remained higher the entire time. It did finish around about 92, while our training data finished about, I'd say, about maybe 90, a little over 90%. Again, the slope wasn't as steep on here of the increase, but that is, like I mentioned, to be expected when you already start out so high. So I was pretty happy with the scores we got. I did want to just take a look and dissect kind of just how our model really worked on a deeper level. So I went ahead and I made a confusion matrix over here to kind of see what drawbacks we had. It's a little bit small, but as you can see here, the most common mistake was basically labeling a t-shirt top as a t-shirt. That happened about 180 times on this validation set, which is pretty understandable error, I would say. And the second most common error was actually mistaking a shirt for a coat, which happened about half as much, happened about 87 times, so about half as much as our most common mistake. Other than that, you know, you can see a lot of zeros in here, so there's a lot of perfect records for, or well, mistakes that weren't made, I should say, but I thought that was pretty useful information to have. Moving on, I also went ahead and printed out a little classification report over here. Take a look at the precision and recall scores. I was pretty happy with the F1 scores here. Most of them are in the 90s, a lot of them in the high 90s actually. Our highest performing ones were Class 1 and Class 8, which are trouser and bag, respectively. But that kind of makes sense. You know, both trouser and bag have pretty recognizable or distinct shapes as compared to the rest of the data. And like I said, this also kind of showed some of the more understandable mistakes. Class 6 had our lowest F1 score, which was still pretty high. It was 0.79. Class 6 was shirt. So we already kind of saw in the confusion matrix the mistakes that were made with shirt. But like I said, I feel like that kind of makes sense, that when we resized the images, the shirt images did kind of look like the coat images or t-shirt / shirt images. So I think like even a human would make some of these mistakes, what I'm saying. But I did decide to just go ahead and print out and display some of the errors that they made. So these are a couple examples. So as you can see, some of these images, I mean, I don't know how it didn't get this show, but you know, for over here, this was a jacket, but they predicted it to be a pair of pants, as you can see, which I can kind of see that they would think that it was a pair of pants, or the model would make that mistake. In my opinion, it actually just looks like a scarf. But you know, with some of these, I think that there are ways that we can fine-tune the model so that it doesn't make all of these mistakes again. But for some of them, I think that it's kind of just going to happen. It's inevitable. And the last thing I decided to do was actually taken from a paper by Chalet in 2017. That was just looking at the activations of the convolutional layers and visualizing what they look like. So the first first convolutional layer, the activation looks like this. So kind of a vague, blurry outline of a shirt. So I went ahead and examine the activation of this second layer, the first channel. Over here you can see it's a little bit more vague. So after I looked at these, I decided to just print them all out. So over here you've got all 4 layers, conv2d1, conv2d2, conv2d3, and last but not least, conv2d4. As you can see, the shapes kind of get more general and more vague the deeper the layers go, but you know, this makes sense. All these are basically just little filters, each responsible for identifying one part of the image and labeling it in its class. I wasn't able to interpret the layers, I think, as in-depth as I will be in the future, but I think that having this information could help in, you know, fine-tuning our convolutional neural network someday. Which brings us to our conclusion. So to reiterate our findings, between the 2 models, the highest accuracy score was actually for the initial model that was fit before we augmented the data. Model 1 had a score of roughly 93.5 accuracy, and Model 2 had a score of roughly 92.5 accuracy. Model 1 had a loss of 0.18, and Model 2 had a loss of 0.2. And the model struggled mostly with the identification of class 6, which was shirt, which again makes sense considering how similar some of the items were to that. In the future, with more time and resources, I think it could be both interesting and rewarding to play with the parameters of the convolutional neural network more, you know, really learn more about fine-tuning, adding additional epochs, which as we know can definitely increase the accuracy score, and perhaps even try loading the CNN that we build on another data set, such as the M-NIST. In researching the project, I also found that there actually is a way to enhance the recognition of images through pre-processing. So using a package like Skimage, which can actually just kind of clean up some of the more blurry lines in these images. So I guess that would kind of fall under the category of data cleaning. But that, I guess, concludes my first computer vision project. Alright, thanks.